Hello everyone, Deep Learning with Python, chapter 4. So today we will go through this chapter. Let's see the title and the contents. Getting started with neural networks, classification and regression. So let's see what we will see today. Here are the chapter contents. So we will see our first examples of real-world machine learning workflows and learn how to handle classification problems over vector data, and also how to handle continuous regression problems over, again, vector data. So the idea is pretty simple. We will go through three different problems, three different tasks, and see how we can approach them. The first one will be a classification problem where we will have movie reviews. So I guess you are familiar with IMDb, the movie database. So we will get reviews from this database over different movies, and we will try to classify these reviews, these texts, as positive or negative. So this is the first task. The second one that we will go through will be the classification not on two categories, but on multiple categories, so multi-class classification. And this one will be on news wires from Reuters. So we will have again the text, the short description, the newswire, and then we will try to classify in one out of many categories. And the last one will be a regression problem. So in this one, we will have data for different houses in Boston area. And based on this data, like how many square meters, when it was built, etc., we will try to estimate the price. So a regression problem, price estimation. So let's start. So the first task, classifying movie reviews, a binary classification example. As I mentioned before, we will use the IMDb dataset. So a good thing, this dataset also comes with the keras. So we just call tensorflow.keras.test datasets, and we can import IMDb. So again, the same way we loaded the MNIST data, we call IMDb, which is a dataset, .load data. And here you see one difference is that we use the number of words, num words, to be 10,000. What this means is that from all the, so there are texts that have different words. We take all these words and we keep the 10,000 most frequent words, because there are some words that appear only once or twice. So if we include everything, the vocabulary will be very big. And this is why we usually cut it out to 10 or 20,000 words, the most common words, the most frequent. Now this returns the usual tuples. So the first will be the train data and labels, and the second one will be the test data and labels. So let's run this one and see what they look like. So this is the train data. This is already a bit pre-processed. We will see how we can deal with raw text data in chapter 11, where we will have the original words. Now what we have is the indices. So we have this vocabulary of 10,000 words, and then we have the index of the word that appears. So if the word the is the fourth word, we have the number 4, etc. So in total, we will have 50,000 reviews, both train and test, from the Internet Movie database. So two categories, and the good thing is that it's already balanced. So we have 50-50, 50% negative, 50% positive. Now let's continue. Let's see what the train labels look like. So the label for the first review is a number 1. So it will be either 0 or 1. And as expected, the maximum index will be 9,999, and this is because we have a total of 10,000 words in our vocabulary. So the maximum index for the vocabulary will be this one. Now, let's continue. Let's see how we can decode a review back to a text. So we have the numbers. Let's see how we can understand what is written there. What we can do is that we can call imdb.getWordIndex, and this will return a dictionary. So this dictionary has the word as a key and the index, the number, as the value. And what we will do is that we will reverse this dictionary. So here is this reverse process where we reverse the key and the value to be value and key. And then we have the decoded review where we get each word of the list. We join the words with a space and we have the index of this word. Now you notice here that we have I minus 3, and this is because the first 3 indices, index 0, 1, and 2, are reserved for specific cases. 0, we will see in the future, is for padding. 1 is for the start of the sequence, so the first character. And 2 is for unknown words, so words that are not included in the 10,000 words vocabulary. So if a word is not included, we also put this question mark. Now let's see what the first review looks like. So this is the first review decoded. And here you can see the text. So it's a normal text review. We start with something, this film, etc., etc. So you see that there are some unknown words. So these words, again, are words that are not included in the 10,000 words vocabulary. So now that we see what this dataset look like, again, we have these reviews and we have 0 or 1, negative or positive. Let's see what we can do with this, how we can treat this and create a classifier. Let's prepare the data. We said that the first step is to prepare the data and then deal with the model. So in this case, we have each review is a vector of n characters. It can be different number of words, different number of numbers, right? So a small review will have fewer, bigger will have more characters. What we want, since we are making patches of these samples, is all of them to have the same length. So we have to figure out a way to make these different length reviews to be the same length. Now there are two very common ways to do this. One is padding, which means that we define a fixed size. If there are more words than this size, we cut them out. If they are less, we pad with zeros. So this is one way. The other way would be what we will do actually right now, the multi-hot encoding. Now what this means is this thing. We define the encoding, which has the dimension 10,000, the same as the vocabulary. And then for each sample, we set 1 if at this position, the word at this position appears in our review, and 0 if it doesn't appear. So this is a multi-hot. And this is what takes part here. So it's zeros initially everything. And if the word exists, we put 1. And then we take the train data and the test data, and we create the vectorized sequences, which is the X-train and the X-test. Let's run this one and see what it looks like. So for example, the first sample, the one that we saw with different numbers, different integers, now looks like a 0 and 1 long, 10,000 long vector. So doing this, we know that each review will have the same length. And now we are ready to feed this input data to the model. Also, what we have to do is the labels to transform them from integer 64 to float 32. This is just for making it easier for the model. So let's run this one too. And now we have both our X and Y, train and test data, to be pre-processed and prepared for the model. So we can move to the model. Now, since we have a model that takes vectors, 10,000 dimension of vectors, and returns scalar, one very, very simple approach that we will see now is to stack some fully connected layers. So let's see the definition of the model. The idea is that we take as input vectorized text. So again, 10,000 length. We will pass it through a series of dense layers, and we will get as output one number that should be between 0 and 1 to compare it with 0 or 1, which is the level. Now we will use dense layers. We will start with 16 units for the hidden layers, and of course 1 unit, 1 output number. And here we can change, we can play with how many layers we will use or how many units per layer. We will see some differences later on. So let's continue and see the code. So we have already seen this part. We import keras and layers. We will use keras.sequential since we have a sequential model with 3 layers. Dense, all of them, 16 units, 16 and 1 output. And for the activation, we have ReLU for the first 2 and Sigmoid for the third. Let's see what are these activations. So I mentioned this before, just to review this again. ReLU is a function that takes any number and makes it, if it's positive, it leaves it as is. So if it's 1.5, it will stay 1.5. If it's 0.5, again 0.5. But if it's a negative number, it will be 0. So it's the max between 0 and the number. And sigmoid, sigmoid is a function that takes any number, positive or negative, and transform it to a number between 0 and 1. And this is because we want the output to be probability between 0 and 1. Okay, so this is very common when you want one probability. So let's continue. After we build the model, we want to compile the model. So pretty straightforward. We will use a simple optimizer, RMS prop. For loss function, since we want to compare probabilities, we use cross entropy. It's quite common when we compare probabilities to use cross entropy. And since we have 2 probabilities, 2 cases, 2 classes, we use binary cross entropy. And for the metrics, since our dataset is balanced, we can use accuracy and it will be more or less good. So we have prepared the data, we have built the model, and we have compiled the model. The next step will be to split the data. So if you remember, I mentioned also last time that it's a good practice to not use the test data for your experiments, to use the test data only in the end. Any decision that has to do with hyperparameters, like, for example, what kind of model to use, how many layers, how many units per layer, what kind of optimizer or what kind of loss function, or what exact pre-processing, all these decisions that I mentioned before, and we can change them, it's good to make them based on a separate set, which is called validation set. So what we do is that we take the trained data and we split them to train and validation. We check how the performance is at the validation data that the model doesn't see during training. And based on this performance, we can tune these hyperparameters. So this is a very common strategy. So let's set aside some validation set. The data are already shuffled, so we don't have to shuffle this time. We will just take the first 10,000 to be validation, both for the X and the Y. So, and we keep the rest from the trained data as partial train. So now we have the model, we have the data, we have made the split for the validation, we just have to train the model. So training the model in Keras, again, it's very easy, it's just one line. It's this function, model.fit. First element, again, is the train and the inputs. Second element is the targets. Then we have the epochs, we have the batch size, and we have the validation data, which is a tuple with X and Y. Okay. So based on this, we will get the history. Let's see. First of all, it will run quite fast because it's a small model. And it returns the history. So history, we show it again. Okay, I have to go, I guess, like this. Okay, so now I can scroll. So this history object has this field history, which is a dictionary, the history dictionary. And let's see what is in this dictionary. So here we have loss and the metrics. We only have accuracy, both for training, these two, and for validation. Let's see how because I mean, we can check these numbers, but it's easier to plot them to see how the training went, okay? So let's plot the loss, both for training and for validation. In order to plot, again, we can use a pyplot, and we just take the loss and the value loss. We define the x-axis to be the epochs. We use blue dots for train and blue line for validation. And we just set the title, the X and Y label, the legend, etc. So this is just to plot this. And what we can see here, so this is the important thing. We have the loss. Again, the dots are for trained data. And we see that the loss for the trained data reduces and continues to reduce almost to 0. Okay, so this is very good for training. But for the validation loss, this continuous line, this blue line, we see that it reduces for the first, I don't know, 5 or 6 epochs, but then it starts to increase, which is bad. I mean, what we want is to keep decreasing, right? Now let's see what happens with the accuracy. So is something similar happening? Let's plot the accuracy. So more or less same thing, but now for the accuracy. And we see that again, the train accuracy increases and reaches almost to 1. But the validation accuracy at some point around here, the 4th or 5th epoch, peaks and then starts decreasing, which again is bad because we want the model to perform well not only on the trained data, but also the validation data. Now, this is a very common thing, and it's called overfitting, if you're not familiar with the term. And this means that after the 4th epoch here, the model over-optimizes on the trained data, which means that it doesn't learn the patterns, it learns to memorize the data. And it knows that, okay, if I have this vector, this will be the output, but doesn't know why. It doesn't understand the patterns of why, so that it can generalize good on the validation data. And this is a common mistake, a common problem, and we will see different ways to counter this. But for the moment, what we can do is just train for that many epochs and stop it here. So let's retrain the model from scratch. We build the model, same exact model. We compile with the same exact parameters. And we fit, but this time we will fit only for 4 epochs because we saw that around 4th epoch, it's a peak, right? So this change, the number of epochs, for example, as well as other kind of changes that we might have done, is due to the validation set, okay? And you see here that we don't split, we don't use the X-train and validation and the validation set. We take all of them, we train it, and then we run on test set to get the results. So here, the idea is that we evaluate on X test and Y test, and we see that we achieve something like 88.6% accuracy. Now, this is not perfect, but it's not that bad. I mean, actually, the state of the art for these data sets is around 95%. We are above 88%, so it's good. I mean, it took a few minutes and we have a quite good class 5. And it's based on text, based on words. It's something that people can use. Okay, so this was a very short example of what we can do with text data. Let's see what these results look like. So again, the first number is the loss and the second number is the metric, in our case, the accuracy. And let's see how we can use this trained model that we got right now to generate predictions again on the new data, the test data. So we call model.predict as we saw before, and this will return one number per sample. We have, I don't remember how many test samples, but the idea is that the first number corresponds to the first sample, the second to the second, etc. So we can say, okay, if this number is less than 0.5, it's negative, otherwise it's positive. And it's very easy to classify new text this way. So we saw a specific way of approaching this experiment, this task. Now, let's see what further we could have done with this. So this is all we have done. We have defined the model and these parameters for compilation and these parameters for the fit of the model. What we could have changed here is, for example, how many hidden layers we have. Instead of 2, we don't count this one, the output layer. So instead of 2, we could have 1 or 3. So we can see, okay, if I add 1 more here, will it be better or worse? Or we could change this number to say, okay, instead of 16, I want 32. Okay, so what changes? Or 64 and here 32. So you can make these changes and try it also by yourself and see, okay, does it become better, worse? And this is more or less the way that it works. And in the end, you just call model evaluate after you have fixed this to see if the model gets better. Another thing you could change is the loss function. For example, instead of binary cross entropy, which is more or less a standard, you could have used a mean squared error. It also works because you have two numbers and you take the square error between the two numbers. A different thing to change is the activation. For example, instead of RLU, you could use tan 8, which was used before RLU either way, quite often. So there are many things you can tweak, many small things, and we will see more things in the next chapters, how you can change the whole architecture of the model, how you can regularize it, etc. So let's wrap up what we learned in this for this task, for the first out of the 3 tasks, and move to the next one. First of all, we saw how we pre-process the data and whether we need to pre-process data. Specifically, in this case, we couldn't not pre-process because, again, they have to have the same length, all the data, the same shape, all the samples. In our case, we used a multi-hot encoding in order to pre-process the data. Also, we used for the model dense layers, so just stack dense layers with RLU activation for the hidden layers, which is again quite often. Now for binary classification, which was this task, the output, the last layer, is almost always dense layer with 1 unit as output. And we use sigmoid as the activation function. This is pretty much the standard way to do it. And for a very common loss for this is, again, binary cross entropy. Now, for the optimizer, RMS prop is a generally good option. You can use Adam if you want. We mentioned it at the last session. And we also saw the very important problem, which is crucial in the core of deep learning that we have to counter, is overfitting. Again, it's when the model performs good at training data, but after a point bad at the validation data. And this is why we have this split of train and validation. Now, this was for the first out of the 3. Let's move to the second. So the second task that we will deal with today is a multi-class classification example, multi-class classification problem, and we classify news wires. So the idea is that we have data that come from the Reuters dataset. So we have short news wires and their topics from the Reuters published in 1986. We have 46 different topics, 46 different categories, and the data are not balanced. We don't have same amount of samples for each topic. Let's see the dataset. First of all, again, we are lucky because we don't have to download or do something. It comes with TensorFlow. You just call tensorflow.keras.datasets import Reuters. Again, Reuters.load data returns the usual tuples. And again, we use 10,000 as num words argument. And this is, again, because we want to limit the total vocabulary of known words to 10,000. So let's run this one and check the data again. So we know the drill. We see what the trained data look like. So we have 8,982 samples for training. And we have 2,246 samples for test. And let's see what the first train sample looks like. It's more or less the same as the previous example with the IMDb, the reviews. It's just numbers, one number, one word. Now, let's decode. We will use the same way to decode as before. So let's see what it looks like. And here is the first newswire. So we have some unknown words, someone said something, and you have the text, okay? So very similar to the previous one, the difference lies in the labels this time. So the train labels, instead of having 0 or 1, here we have one number out of the first 46. So this is at the 4th topic. So we have the index 3. So let's see how we can deal with this kind of multi-class classification problems. First of all, let's prepare the data as before. We will start with encoding the input data, and we will use the same function as before. We just want multi-hot encoding. We already have the function, we use it. And then we have the encode, we will also, this is different. So here we have the encoding of the labels. So before we didn't change the labels, we just made them float. Now here, we don't want the model to predict one number. So it's not like, okay, we have numbers from 0 to 45 or something like this, and we want the model to output one number, and if it's close to some integer, then it's this. It doesn't work like this, and it doesn't work like this because it's not a continuous value, it's not ordered. So topic 3 is not closer to topic 4 than to topic 6, right? So it's not that if it's close, it's more similar. And if it's, for example, the model would output 3.4, it doesn't mean that it's a topic closer to 3, but also to 4. So we cannot just output one number and hope it will be the correct. The way we treat multi-class problems is with one hot encoding. So we have the model to output 46 numbers between 0 and 1, and we keep the one that is the highest probability. And thus, we have to transform the targets, the ground truth data, to one hot, which is, again, we have zeros everywhere and 1 at the position of the topic. So this is how we do it. We transform the train labels to white train and then to white test. And actually, we don't even have to use this. TensorFlow has the two-categorical function that takes the numbers and transform to one hot vectors. So this code here has the same result as this code here, just this is faster. So this is for the targets. Now let's build the model. Let's define the model. So here we see some differences. More or less it's the same. It's a stack of 3 dense layers. Again, we have ReLU here. Now one difference is that here we have softmax. Now it is softmax because we want the model to output 46 numbers, all numbers to be between 0 and 1, and the sum of them to be equal to 1. And this is because there is only one correct answer. If we have multiple correct answers, then we would use a different activation here. It would be sigmoid, for example. But in this case, we have one correct answer out of 46, so we use softmax. Another difference is the number of units at the previous layer, at the hidden layers. And we see that we want to output 46. Now, if we had here, for example, 16 or 10 or whatever, then we might have the problem that we have an information bottleneck. So we don't want to shrink the information too much at the hidden layers and then expand it at the last layer. This might drive to losing some important information. And this is why we keep higher number here than here. We will see actually a variation where we don't do this and what happens. So let's compile the model, RMS prop. Now here, again, we want to compare probabilities. So we use cross entropy. But in this case, we have multiple categories. So we use categorical cross entropy since we have one correct out of many. And for the metrics, we will use again accuracy. I know it's not balanced, but well, it is what it is. I don't know if there is a better metric for this, and accuracy is pretty much simple. How many did we find correct? Now, same as before, we want to split the validation data. So in this case, we have fewer data, so we will split fewer. We will keep the first 1,000 out of all the training data. And this is more or less what we did before. And let's move to training the model based on these parameters. We will train for 20 epochs. We will see if it's enough or not based on the curves, based on the validation data. So let's train it. Nothing new here. We train the model. Yeah, I have to do this. And it's already done. And now let's plot the data. So we'll start with the loss function. This code is same as before. You don't have something new here to explain. And we see more or less what we saw before. So train loss goes down. Very good. Validation loss goes down, but then stops around here at, I don't know, 9 or something, and then stabilizes. So it doesn't get any better. And the same for the accuracy. Let's see the accuracy curves. And same as before, it increases, training very good, validation data, it reaches some peak, I don't know, here or here, so somewhere here. So 20 epochs is more than enough. What we can do is retrain the model with the fine-tuned parameters. In this case, we will just fine-tune the number of epochs. And this is just to show why we use validation. So it's very, very simple variation. So let's train for 9 epochs and see the results. So we keep everything the same and we just change one thing. And this is actually something that we do quite common, that we make one change, we run the experiment, and it's better to run more than once because it's not that it will stay the same. And then see, okay, did it get any better or not? Because in many cases, we change many stuff, we get a better result and we say, okay, this big package worked. Okay, but then we don't know what is necessary and what is not, right? So small changes, one change per time, see does it work, does it not work, etc. So no, here. And let's see the results. So loss and metric, in this case accuracy, and we have something like 79.8% accuracy. Now we don't know if this is good or bad, right? I mean, usually what you do when you have a new task is to set a baseline to say, okay, I expect that if I had a dummy, very, very dummy approach, I would have at least this performance. And then run a very simple experiment and see, okay, do I have better results than this? Because if it's worse, it doesn't worth this thing. I can do it with a dummy way. So in this case, a dummy way would be to just output random. So let's say that we have these 46 categories. We have, I don't know how many samples per category. And let's say I just shuffle the labels and see how many are correct, which is what we do here. We shuffle them and we see, okay, how many are the same before and after. And this is a very, and if we take the mean, we see what would be the bottom line. So what would be the baseline for the worst case scenario that we could have. And we see that worst case, we could have at least 70% accuracy. And so this is quite good, actually, in comparison to the baseline. Of course, we could have better baseline to take everything to be equal to the category with the most samples. This would be a way. So we will talk about the baseline in the next chapters, and we will see why it's very important, because in some cases, again, the baseline is very hard to beat. We will see some examples with the weather. So let's move now to generate, see how, again, we can generate predictions for new data. It's more or less the same. We just call model.predict. The difference here is that predictions has 46 numbers. It's not one number. And the sum of these numbers should be close to 1. Okay, more or less. So this is probabilities for each one of the categories. So what we have to do, we saw it again in the past, we have to take the maximum argument. So argmax will return the index of the item of the list or the array that is the maximum. And we see that here label with index 3 is the maximum, which means that we would categorize as the fourth topic in this case. So this is how you can predict on new sample, on new newswire. And this was more or less on training, fitting, evaluating, and getting the prediction for new data. Now let's see what I mentioned before, what happens if we have small intermediate layers, so the number of units, if we have a bottleneck. So we have the same parameters here, but we change this. Instead of 64, we have 4, which means that there is a bottleneck. Let's see how will this perform. So we train the model from scratch. and it's trained, should be trained more or less. Okay. I don't have the, yeah, you can see here. So more or less we have 71.5 and the previous was 78 point something, I think. So we have some 7-8%. Usually it's around, if you run it again, around 8% absolute drop, which means that it's not that it cannot learn things, it's that it loses information. So 4-dimension is too small as an intermediate space. It's too low dimension and it cannot, it cram most of the information, necessary information that is needed, but not all of it that it could. And this is a very simplistic example of avoiding why you should avoid information bottlenecks. Now, for further experimentation, you can again have more or less number of layers, the number of units, so pretty much the same thing as before. Now, wrapping up, let's see what we learned from the second experiment. First of all, the difference from the first one, the main difference is the number of classes. So instead of 0 or 1, here we have n classes. And this is why the last layer should be dense with n units. Now, the activation of the last layer, since we have only one correct answer, is softmax. For the loss function, we use categorical cross-entropy. Again, cross-entropy because we try to minimize the distance between the probability distributions. Regarding the encoding, we used for the labels one hot. So if you don't want to use one hot to have the integers as a target, it is possible, but in this case, you should use sparse categorical cross-entropy. So this will take the one hot of the prediction, will transform it to, it will actually take the target and make it compatible to compare with the prediction. So it is, you can do it. And then the last thing is what we saw before, that you should try to avoid any information bottlenecks in the hidden layers. So this was more or less for the second out of the 3 tasks that we will see today. And let's move to the third one and see what we can learn from this one. This one is very different than the first 2. Here we have a regression problem. So a few words for the, first of all, let's see what is regression, then I will describe shortly the dataset. So regression is when we try to predict a continuous value instead of labels. For example, if we want to predict temperature that we will have tomorrow, given some meteorological data of today, temperature is a continuous value, so we have a regression problem. If we want to predict how much time it will take for a software project to complete, given the specifications, this, since time is continuous variable, it is a continuous, it is a regression example. So in our case, we want to predict, as I mentioned before, the price of the houses of a specific area. So we have the data from the Boston suburb area from mid-1970s. We have few data, we have only 506 data points total. And we have, I think it's around 13 features. The problem with the features is that each one is in different scale. So there are some features, some numbers for each sample that are between 0 and 1, some numbers that are between, 1 and 12, some numbers between 0 and 100, etc. So we will have to see how we can deal with this kind of different scale. Okay, so let's start by loading the Boston housing price dataset. Again, it comes with keras, so Boston housing .load data, we don't have to define any here. We take the train data, train targets, test data, and test targets. Now let's see what they look like. Train data, we have 404 for training, and they have 13 features. For each house, we have 13 numbers. And we have 102 samples for testing. And let's see what the targets look like. So the targets are numbers that are thousands of dollars. So for example, the first house, the price would be $15,000, more or less. So of course, these prices are from mid 70s. It's not, it doesn't take into account inflation. So this is why they are like this. And let's see how we can prepare the data. So we show what the data look like. And I mentioned that we have the problem of different scales. So let's see how we can normalize the data. This is very important, and it's quite crucial in some projects to have the correct normalization, the correct pre-processing. So a very common thing to do when we want to normalize data, especially when we have different scales. Actually, let's see the scales. I mean, let's see. So train data, let's see the first one. So you see, we have numbers that are close to 1 or 0, close to 8 or something. We have numbers up to 90 something, 396. So these are very, very different scales, okay? So this is what we usually do. For each one of these 13 features, we'll take the average and we will subtract from every sample for this feature, the average, and divide by standard deviation. This mean and standard deviation approach for normalizing is very common because then after this, all the data will be on average centered at 0 and have standard deviation of 1. So this is how we do it. Pay attention here, we use trained data only in order to normalize. We don't take the standard deviation and the average of the test data. So we take the mean of the training data for 0 axis, we subtract it, and then we take the standard deviation of this, again the same axis, because we want for each feature separately. We get the standard deviation, and then we divide the trained data that are centered with the standard deviation to have standard deviation 1. And keeping the same mean and the same standard deviation, we normalize the test data. Okay, it's very important not to recalculate these two numbers for the test data, because then you will have some information leak, which we don't want. Okay, so this was more or less the pre-processing. So this was for the inputs. Now the targets is just numbers, so we don't have to make any pre-processing. We just feed them. They are already float numbers. So let's see what kind of model we can use in this case. First of all, because we will have a different approach now, we will define a function that will return the model, because we will want to build again and again. In this case, we will have a sequential 3 dense layers like before, 64. We want, okay, I mean, here it's pretty much arbitrary. You can try different numbers. What is important is that here you don't have activation, and you don't have activation because you don't have to limit the output of the model to something. You don't have to limit it to be between 0 and 1, or to be the sum of probabilities or something like this. You just want it to output a number, and you wish this number to be close to the target. How many thousands of dollars for each house? And so for compiling, we have 2 differences here. We don't use cross entropy. Again, cross entropy is when you're going to compare probability distributions. Here we want to compare prices. So we want to see what is the difference between the predicted price and the real price. So we can use mean absolute error. So take the absolute difference for all the samples and take the average. Now we could use this one here, but it turns out that the mean squared error is a better loss function. It works better, so we use mean squared error for loss in this case. Now, the reason we don't use mean squared error here too is that dollars squared doesn't make any sense. I mean, it's what, or time squared. We cannot understand what this means if we had a $15 squared. But if we have 15 as absolute difference, we know 15, okay, 2, we know that we are more or less $2,000 away from the price on average, okay? So we have the function to build the model, to call it. Now, as I mentioned before, we have very few data, okay? We have around 400 samples. So usually we have thousands of them and we can run the model and split validation, etc. Now we don't have this, we cannot afford splitting out 100 data and keep only 300, and that would be all. So one approach when you have few data is k-fold validation. Let's see what this means. This means that what we do, actually it's more or less what we do. So we split some parts for validation, but we do it many times. So we take all the data, we define a number of folds. In this case, we have 3 folds, 3 partitions. So we split the data in 3 parts. And every time we keep one part for validation and all the other parts for training. And we run it again and again, and we use all the parts as validation at least once. Then we take the scores and we average the final score and the scores to get the final score. And this final score is more representative of what the result would look like. And this is the number that we use in order to fine-tune the hyperparameters. Let's see it in practice. So here is the code of how to perform manually a k-fold validation. There are actually ways to perform it with one line with Python libraries. But here is what actually takes place internally. So we define how many folds we will have. Like here we have 3, we will have 4 this time. We also define the number of validation samples. So how many we have divided by how many folds. And here is the hyperparameter, so how many epochs. And then for each fold, we repeat this process, okay? So we define the all scores to be a list to add the final score for each fold so that we can take the average. And we split the data, so we keep this part, this slice as validation, both for the data, the inputs and the targets. And then we concatenate all the other data to be the trained data and the trained targets. So this is the splitting part. We define the model, we take it from the function I showed before, and then we fit the model using this partial train targets, the number of epochs we have, nothing new here. We don't want to print the progress bar. And then we evaluate and we take the mean squared error, the mean absolute error, and we just care about the metric, the mean average error. So let's run this. This will take some time. So now we are processing the first fold. And what we will see is that actually there is some difference between the folds, which means that, which is something that we expect. We have few data, so there will be some deviations from fold to fold. And this is why we get the average of this, to have a better image of what happens. So these are all the scores. We see that we have numbers as low as 1.98 and as large as 2.78. So you see that there are quite big differences. Now let's see what is the average of it. So the average is 2.37. So it means that when we have a new house and we want to predict the price of the house, we will be more or less $2,300 away on average from the real value. Now, it's still quite a big difference in some cases. So what we can do is to try to train for more epochs, for example, okay? So what we will do here is that we'll do the same thing, but for 500 epochs to see if we can get any better results in the future. But we will also keep for every epoch these numbers, the absolute errors for each fold, so that we can plot then the average absolute error of all the folds per epoch. Now we'll not run this experiment now because it takes more than 3 minutes and we will just see each other for 3 minutes. I have already run it and I have already gotten the results. So if you get the average, I mean, if you get these, let me show what was before. So what we do is that we have defined the all mean average histories and we take for each epoch and for each for each fold, all the history that has for all the epochs, the data, and we keep the validation mean absolute error, and then we add it to this list. So what we will do now is that we will take this data and we will take the mean per epoch, okay? And here you can see what it looks like if you plot it. So again, x-axis is the epoch number, and y-axis is the average for all the folds, all the 4 folds. And of course, you cannot see anything here because the first numbers are very high and you cannot see the difference. So let's cut out the first 10 data points and plot again. And here you can see that we want, first of all, it's absolute error. So we want it to be low. And you see that there is somewhere here, maybe the best result. So it gets down and after this point it starts getting up. So overfitting happens after around this area. So this is why we use this k-fold in order to fine-tune some parameters. In this case, we fine-tune the number of epochs. So 100 might be few, 500 is definitely too much. We will train it for somewhere here. So what we will do is to train the model for 130 epochs. And since we have fine-tuned all the parameters, we just train it on all the trained data, all the trained targets. We don't keep any data for validation since we don't want to validate it. And then we evaluate the final model, the trained model, on the test data and the test targets. And we take the mean, the test mean squared error and the test mean absolute error. And it looks like this. So we have after this, for the test set, 2.36 average mean absolute error. Now let's see how we can generate predictions. It's more or less the same as before. We get the model dot predict and the samples that we want. And this is, for example, for the first sample. And we see that the price that it predicts is around 7.87. Now let's wrap up this last task and how we approached it. First of all, it was a regression problem. So what we do is that we use for loss function mean squared error and for metric mean absolute error. We have feature-wise normalization. So for each feature, we subtract the mean and we divide by the standard deviation. And we do this, calculate the mean and the standard deviation on the trained data, okay? Then we have since we have few data, we use k-fold. K-fold is a good approach for few data in order to tune the hyperparameters like the number of epochs. And again, since we have few data, we use a small model because if we had many layers, we will see that it will start overfitting too fast because it will just remember all the cases. I mean, we have 300 cases per fold, so it would be very easy for the model. So this was for these 3 tasks that we saw today. Let's summarize what we saw today and close this session because it's already time. So binary classification, the first task. Multi-class classification was the second class. So the second task. So the first task was the IMDb, the texts for the movies, and we classified them as positive or negative. The second one, the multi-class classification, was from the Reuters, the newswires, and we classified them as at which topic out of the 46 topics. And the last one was scalar regression. We tried to estimate the price for a house based on some features of the house. We learned how to pre-process the raw data or almost raw data. For the text, we will see how to process the actual raw data in the future. We also learned that when we have multiple different features in different scales, we can do feature-wise scaling. We also learned what overfit is and that it actually happens to everyone. It's not your fault. After a point, the model performs better at the training data and worse at the validation data. And also, if we have a small data set, like in the third example, it's actually also the other ones, it's not that big. It's better to use small models. And what small model means, it's not something specific. Again, you try and you change and you try and you change and you see more or less what works. Again, it's engineering, it's not science, most of it. So formatic class problems, remember not to have bottlenecks, information bottlenecks in the hidden layers. So if you have many classes, don't have very small hidden layers. And also, if you have few data, what we learned is that one very good approach and very common is to use k-fold validation in order to search for good parameters. And after you have found these good parameters, again, as an example, the number of epochs, what you have to do is to use all the data, train on all the data, get a final model, and it is what it is. So that was more or less, this was the end of the presentation in this session. Thank you very much.